In this video we look at when two self-adjoint operators, A and B, can be diagonalized simultaneously. It means the existence of an orthonormal basis in Cn, which consists of common eigenvectors for both A and B. The condition is that AB commute. This gives a spectral decomposition for normal operators, since the latter is a combination of two commuting self-adjoint operators. As an application, we may characterize positive operators. These are self-adjoint operators with positive eigenvalues. We use the same notation. The space will always be finite-dimensional. The inner product is linear in the second variable and conjugate linear in the first variable. A column vector in Dirac's notation is a ket vector. A row vector is a bra vector. Ket bra gives a rank 1 operator. Suppose A and B are both self-adjoint. We would like to find common eigenvectors for A and B, so that they form an orthonormal basis of Cn. Let's say A has eigenvalues, lambda 1, lambda 2, up to lambda n, and B has eigenvalues mu1, mu2 up to mu_n. If U is the unitary matrix containing those common eigenvectors, then the question is equivalent to these matrix equations. AU is equal to U times a diagonal matrix dA, which has the eigenvalues of A on the diagonal. Similarly, the U is equal to U times dB. Therefore, A and B are both unitarily equivalent to some diagonal matrices. Here is a summary. A necessary and sufficient condition to diagonalize A and B simultaneously is that they commute. When AB equals BA, there is an orthonormal basis in the whole space. The matrices of A and B under this basis are both diagonal and have real entries. The equivalence of 1 and 2 is simply by definition. Next, we will verify 2 and 3 are equivalent. Let's check 2 implies 3. This gives a necessary condition for simultaneous diagonalization. The two operators must commute. Suppose A and B are diagonalized by the same unitary matrix. We look at the product. Since U is unitary, U star U is the identity operator, so the product is U dA dB U star. Similarly, BA is equal to U dB dA U star. Clearly the diagonal matrices dA dB commute, so we get AB equals BA. From the above discussion, if A and B are diagonalized simultaneously, then they must commute. The converse of this observation is also true, and this is the non-trivial part. The assumption is that both A and B are self-adjoint, and they commute. Apply the spectral theorem to A and get the decomposition. The eigenvalues are all distinct, but the projections may not be rank 1. In other words, we use distinct eigenvalues, and the eigenvalues could have multiplicities greater than 1. In fact, B commutes with every projection. For example, let's verify that P commutes with P1. Apply A to B P1. Since A and B commute, this is equal to B A P1, which is the same as lambda 1 B P1. Now we end up with this equation. It means that B P1 is in the range of P1. In other words, B P1 equals P1 B P1. By taking adjoints on both sides of this equation, we get B P1 equals P1 B. Similarly, B commutes with all the other projections. Let's summarize what have been proved so far. In particular, if B commutes with A, then B commutes with every projection in the spectral decomposition of A. Take K equals 1 for instance. Let B1 be the restriction of B to the range of P1. If X is an eigenvalue of B1, then AX equals lambda 1X, because X belongs to the range of P1, on which A is simply the multiplication by lambda 1. Define B1, B2, up to BR. Each one is the restriction of B to the corresponding eigenspace, so each one has a spectral decomposition. Finally, the collection of all the eigenvectors is an orthonormal basis in the whole space. It simultaneously diagonalizes A and B. Let's turn to normal operators. An operator is called normal when it commutes with its adjoint. Every normal operator can be written as a combination of two self-adjoint operators. Remember that every complex number has a real part and an imaginary part. It is very similar here. A normal operator in many ways can be thought of as analogous to a complex number. The two self-adjoint operators commute. To see this, we compute AB, and compare that with BA. Because T is normal, TT star commutes with T star T, so the middle terms vanish. Therefore, AB equals BA. Here is the spectral theorem for normal operators. First, AB are commuting self-adjoint operators. They can be diagonalized simultaneously. This gives an orthonormal basis in Cn, which consists of the common eigenvectors of A and B. Let lambda 1 up to lambda n be the eigenvalues of A, and mu 1 up to mu n be the eigenvalues of B. Then T has complex eigenvalues, Z equals lambda plus I times mu. Under this orthonormal basis, the matrix of T is unitarily equivalent to a diagonal matrix with entry Z1 up to Zn. The above result can be restated by means of projections. When using distinct eigenvalues, the operator T is a weighted sum of spectral projections. The dimension of each projection is equal to the multiplicity of the associated eigenvalue. Let's get back to self-adjoint operators. A special case is when the operator is positive. This means that the inner product of U and AU is greater than or equal to 0 for any vector U. In complex vector spaces, this condition implies that A is in fact self-adjoint. The proof is to verify these two inner products are identical. Using the polarization identity, the inner product of U and AV can be written as follows. By the assumption that A is positive, the inner products on the right-hand side are all real numbers. The vectors x1, x2, x3, and x4 are defined in terms of U and V. We will come back to it shortly. On the other hand, the inner product of AU and V equals the inner product of U and A star V. Now apply the polarization identity again, and get 4 terms on the right-hand side. By moving A to the first variable of the inner product, and using the fact that these 4 interproducts are real, we can flip the inner products, and end up with the same expression. Since the last equation holds for all vectors U and V, the operator A is self-adjoint. Here is the polarization identity for complex inner product spaces. This identity can be verified by a direct calculation. Keep in mind that the inner product is linear in the second variable, and conjugate linear in the first variable. Now we see the vector x1 from the previous step is U plus V. x2 equals U minus V. Similarly, we get x3 and x4. This identity can be written in a more concise form as well. Let's end this video with a characterization of positive operators. Indeed, A is positive, if and only if it is self-adjoint with positive eigenvalues. First, every positive operator is self-adjoint. It remains to check that all the eigenvalues of A are positive. Let lambda be an eigenvalue of A, and let U be an eigenvector of unit norm. Then the inner product of U and AU is equal to lambda. This implies that lambda is positive, because the inner product on the left positive by assumption. Conversely, A has a spectral decomposition, so for any vector V, the inner product of V and AV is given by a linear combination of the norm squares. Since the eigenvalues are assumed positive, the last line is also positive.